Welcome back to the next video, everybody. Today we got a juicy one for you. We're going to talk about passage to quotient. This is one of my favorite topics when discussing finite flat group schemes. Okay, so let's let H be an S group scheme, and we'll let X just be a random S scheme. A right action of H on X, you can do this whole action thing scheme theoretically. It's a morphism A from X cross H over S to X, as expected. And what should it do? Well, it should be such that for every S scheme T, the induced map from X of T cross H of T to X of T, that should be a right action of the group H of T on X of T, right? So it's like a functorial action. And we'll say such an action is strictly free if the morphism ID comma A from X cross H over S to X cross X over S. That's a little bit loose and free with the notation. What I mean is the morphism inducing X comma H maps to X comma XH. So this is a morphism on functors, right? Well, this should be injective, right? If strictly free means what you think it should mean, like from an algebra class, this map should be injective. But we're going to require that not only is that true, we want it to actually be a closed immersion, right? So given a right action of H on X, we'll say that a morphism F from X to Y is constant on orbits if F compose A is F compose the first projection. And both of these are maps from X cross H over S to Y. What's another way of saying this? Why does this mean constant on orbits? Well, if you write all this out, what you see is it means that f of xh equals f of x for all x and x of t, for all h and h of t, and for all t. And so here, you're constant on orbits, right? The image of x and xh are the same under f, no matter what xh and t you pick. Okay, so these are sort of scheme theoretic extensions of definitions from algebra, basically. Theorem, so theorem 1 from Grothendieck. So let's let H be a finite flat S group scheme acting strictly freely on X, where S is just locally Noetherian as a base scheme and X is finite type over S. Okay, and so let's make sure that this happens in such a way that every orbit is contained in an affine open set. We don't want our orbits scattered all over under the image of the action map. Okay, so just think of this as saying the orbits are kind of collected together nicely. Okay, then the category of morphisms X to Z, which are constant on orbits, has an initial object. If you don't know what that means, this is a category theoretic statement. What I mean is there's an S scheme Y and a morphism, let's call it U from X to Y, which is constant on orbits, it's in the category, such that every morphism V from X to Z, which is constant on orbits, i.e. something in the category, admits a unique morphism F from Y to Z factorizing, so such that V equals F compose U. And then by universality, of course, U is unique up to unique isomorphism by the usual nonsense. And we denote this map usually by U as a map from X to what we'll write down as X mod H. And this is called the canonical morphism from F to the orbit scheme, or to the quotient scheme of X by H. Okay, so for a proof of this, see like SGA 3.1, see also Raynaud, Keelan, and Mori have quotients by groupoids, which is a work that exposes much more general results than this, but these are all good places to look. Okay, so in other words, you can do, quotient scheme theoretically, basically. Okay, and I couldn't fit this on the last slide, but this is also part of the theorem. The morphism U from X to X mod H has the following three properties. First of all, X is finite flat over X mod H. And the order of X over X mod H is the same thing as the order of H over S, which is great. Okay, also, for every S scheme T, the canonical map from X of T mod H of T to X mod H of T is injective, as it should be, okay? And then if S is spec R and H is spec B, let's say, so we're working affine now. And let's say X is spec A, so everything's affine. Then it turns out X mod H is affine. It's spec of A naught. And what's A naught? A naught is the subring of A, where the two homomorphisms, the first projection tilde and A tilde, those are both maps from A to A tensor A tensor B over R. It's the subring of A where those two maps agree. Okay. Okay, so why do we care about this theorem? How are we going to use it? Well, the main application of the theorem we care about is the case where X equals G and G is some S group scheme, of course, right? And then we want H to be inside G, just a finite flat closed subgroup scheme, as you probably expected. And then what do we want the action to be? Well, of course, we want the action A from G cross H over S to G to be the restriction of the group law M from G cross G to G. Okay, so this is the situation we care about. Here, when we're working in this situation, we have an even more special name for G mod H. We call it the scheme of left cosets of H and G, as we should. It's a very natural extension of the idea of the group of cosets from algebra. If G mod H is finite and flat over S, then we call its order the order of G mod H over S, the index of H and G, and we write it in the usual algebraic notation, kind of G colon H. Okay, now can we actually get away calling this the index of H and G? Does it have all the properties that indices in group theory have? Yeah, pretty much. Suppose the index of S and H equals M, and that's constant. So suppose we're working in the case where the index is constant. M has to be bigger than 0 because H has a unity section. And so by part 1 of the Grothendieck theorem, by bullet point 1 that I listed after the theorem more precisely, you can conclude that the index or the order of G over G mod H, or the index of G mod H and G, whatever, you conclude that that's also M. And then by proposition 3 from a previous video, we know G is finite flat over S if and only if G mod H is finite flat over S. And when this happens, we have the following string of equalities, which show us that order does behave like we think it does. So the order of G over S, or the index of S and G, whatever, is the same as the index of G mod H in G times the index of S in G mod H. But both of the, we know what both of these are, right? The first one is the order of H over S, and the second one is the order of G over H. In other words, the index of S and G is the index of S and H times the index of H and G. Or if you like, the order of the group equals the order of the subgroup times the index of the subgroup, like from algebra class, right? Let's conclude by looking at all this kind of diagrammatic theoretically. I don't know. The definition of a left action on a group scheme G on a scheme X is now clear from the previous slides. And you can easily check that GX naturally on the left, okay, on the scheme G mod H in a unique way that commutes the following diagram. You expect all this to happen, right? You've got G cross G to G cross G mod H given by ID cross U. You've got the multiplication map M on the left. You've got the left action map of G on G mod H on the right. And you've got the U map on the bottom. Of course, this should commute, right? And it does. Now, if H is normal in G, and what should that mean in this under this setup? It should mean HX trivially on G mod H, right? That's the only thing that really makes sense. Okay. Then there's a morphism from G mod H cross G mod H to G mod H, making G mod H an S group scheme, as expected. Okay, just like what happens in algebra. And our map U from G to G mod H is an S group homomorphism, as expected. And then the sequence from 0 to H to G mod H to 0, where the last kind of non-trivial interesting map here is just U, that's an exact sequence actually, as you expect. Everything just seems to work out very well. Everything just sort of generalizes from algebra perfectly, which is really nice. That's why I like this topic. Now, actually, this sequence here is exact in the sense of this chapter. I have a video on kernels and co-kernels towards the beginning of this chapter, which is several videos ago now. So you should watch that if you haven't yet. But it's also exact in another sense. It turns out U is faithfully flat, which means essentially just means surjective and flat. So it's kind of exact in two different senses. And then H is the kernel of U. So this sequence is exact in a very strong sense, in two very strong senses. And so it appears that we've kind of generalized a lot of basic notions from abstract algebra to the land of schemes, land of group schemes, even more specifically, very well and very precisely. Okay, so I will see you all next week for more videos on finite flat group schemes. So I'll see you then, and thanks for watching.